First of all, hi, and I really thank the organizers. It's my first time in Lisbon, and I'm very happy. It was a great conference. I had work. So for those of you who do not know me, I'm a former student of Stefano. I've worked a little bit about things that can be related to particle systems, about things that can be related to PDEs, but I have only one project that does not relate to any of them, and I will talk about exactly that project. And the price that I will pay for this choice is that most of my talk will be general about definitions. Half of the talk will be non-rigorous, more or less. They can be made rigorous, but I prefer to do them non-rigorously, just to create a little bit of motivation why the model that I'm studying is somehow can be relevant. And slightly at the end of the talk, I will present some result and the model itself and so on. So this is a joint work with Wojciech Drog from KU Leuven. I'm his postdoc. So the plan of the talk is that the first half or even a bit more, I will talk about, so basically I'm trying to define what do I mean by concept of many-body localization. So until now, every talk that you heard was about convergence to equilibrium and creating mechanism how to converge and creating like heat equation as in Stefano's talks and so on. I want to see systems that do not thermalize. And this is a concept of many-body localization that I try to explain. This is something very hot and new in physics. So there are very few mathematical works. So if you get interested, I think physicists will really appreciate, because there is huge fights there. So people really fighting. And then at the end of the talk, I will try to give my model and result. So just to set the notation, probably you've seen this Pauli matrices in Michael talk. So still, as other Stefano's student, I will have chains, but it's quantum. So I have this peculiar notation for Pauli matrices. So the Pauli matrix sigma x acting on site I. So I have n particles. I label them by I, and the Pauli matrix acting on particle I are denoted by xi, yi, and zi. And these are defined this way. So for the first part of the talk, I don't specify the model, but if you want to have a concrete model in mind, you should take this type of Hamiltonian with short range interaction, and Vi is a potential, like this is probably you heard the XXZ chains. So I put a local potential to break any integrability and so on to have a general system. So the concept of thermalization is that, okay, my state space is basically C2 tensor n times. So I have 2 to the power n energies for a big but fixed n. Then I can define the microcanonical energy shell at energy E. So for a local nice observable, so take observable like the magnetization at site I can define the average in a microcanonical shell at energy E, and I denote it by this bracket. And in most of my talk, I'm usually interested in infinite temperature objects. So yes, or highest entropy states. So I define that my system, and my dynamic is the usual Heisenberg dynamic. So I say that my system is thermalizing if I take an initial condition that this initial condition has some average energy E0, then I take a local nice observable, and I compute such Cesaro limit, and if this limit converge into, as time go to infinity, into the macrocanonical average of that observable in energy E0, then I'm saying that my system is thermalizing. And okay, this should be true up to vanishing for, up to errors in n for large n. And to have an interesting example in mind, so take a very peculiar non-equilibrium configuration of spins. So half of your spins are spin up, half of your spin are spin down. You start with this initial configuration, but here the average magnetization should be something like this average between this n minus I and I. So as the dynamic evolve, you should expect as t goes to infinity that the average for last spin will be something like, if you take 1/2 would be something like 1/4 or something of that sort. So as time evolves, you expect for a general system to have long range transport and these spins to be transported over a very long range if you start from peculiar initial configuration. So a bit more refined version of thermalization is something that people in physics community called ETH, or eigenstate thermalization hypothesis. This is coined by Deutsch and Serdinsky in the 90s. This is a much, okay, if it's the first time that you are seeing these things, that they look like very similar, but it's a much strong notion than thermalization. It tells you that all the eigenstate of your system are thermal. So if I take eigenstate and I look at the average of a local observable, that is the key, this really looks like a thermal state, which is rather something very strong. And so there is really no mathematical proof for this in general system. There are a little bit of things that are, okay, there are really some proofs for random matrices. So you see, when you have ETH, this is, people like to call it like quantum chaoticity. So there are some proofs for random matrices, so they have some sort of ETH in some sense. If you have ETH in a system, you get thermalization. And my punchline is that the extreme form of ETH is given by random matrices. So the best chaotic thing is probably in Takeoff-Rida, you became familiar with this GOE and GUE matrices. So the best chaotic thing that you can think of is a GOE matrix. So I completely forget about all these Hamiltonian structures, and the best chaoticity comes from this structure of GOE. Okay, this is a mention of a term ETH. So this thermalization and ETH is believed as classical systems to be a very general behavior. So if you see a model, you expect it to be thermalizing and behave in this sense. So failure of thermalization is something peculiar, is something that you do not expect it in general. So there are examples that we know that thermalization fail, like if you have an integrable system, like take your favorite notion of integrability in quantum system like Young-Baxter, or in a classical system as a total chain, so you have many conserved quantities, so you don't expect your system to be thermalizing. I want to single out the Anderson insulator. So if an Anderson insulator is also a system that is not thermalizing, so it's the first time that you are seeing this. This is a discrete Laplacian in D dimension with on-site random potential. And okay, the discrete Laplacian has discrete Fourier transform as an eigenfunctions, so these are very extended vectors, but as soon as you add a small disorder, your eigenfunction becomes exponentially localized in space, and this gives you that you don't have any thermalization, at least in 1 and 2 dimension. I want to single out this. But the thing that is true about these two examples is that they are non-robust, meaning that if I add a very small perturbation to an integrable system, a local perturbation, or if I add a potential to the Anderson model, at least phenomenologically, physicists believe that they will become thermalizing. So MBL for me is a robust form of lack of thermalization, so with respect to local perturbation. So you have a system, it does not thermalize, you add a very small but fixed local perturbation, and still it's become non-thermalizing. So the first question that you can ask is that, does such a beast exist or not? And this is something that if you ask any physicist in Europe, probably they will have different opinion. But at least the majority believes that it exists. And so the one example that there are many numerical and theoretical evidence to support that it has many-body localization is a disorder XXZ chain. So you take XXZ chain, you take on-site magnetic field HI to be random variable uniformly distributed on some interval. So as this W grows, I have much stronger randomness. And so this first of the Hamiltonian that I denote by Hn0 can be mapped to Anderson insulator by some Jordan-Wigner transform. So this is really an Anderson insulator in disguise, like just writing in a more involved way in other coordinates. And then I add the interaction. And people believe that, okay, when J0 is 0, when Jz is 0, this is Anderson insulator, it's not thermalizing. But people believe that there is a transition in this system as like fixed W. And as you move from 0 to high value for this interaction J of Z, you move from a localized state to a thermalizing state. So this is an example of a localization-delocalization transition. At least numerically, and many strong theoretical arguments support this. No mathematical proof. So just to have a picture, so if you change this J of Z in 0, you have Anderson insulator. As you increase it, you still expect to be in a localized state in some sense, and then you translate to the ergodic system. And when you are in an MBL state and not Anderson, meaning positive J of Z, if you prepare your system that half of your system has a much higher energy and the other half has a much lower energy, and you let time evolve infinitely, you only have a very small effect at the boundary of these two parts. So you would expect that all your system will reach to an average energy, but this does not happen in this MBL case. Okay, the way that people argue that such a thing exists, it's a little bit similar to the integrability. So they construct by non-rigorous perturbative schemes a complete set of conserved quantities, this tau I, so they are conserved, they commute with each others. So this is something that you can do for any Hamiltonian, but the thing that single out MBL is that you can do it with a quasi-local transformation. So I can construct like n conserved quantity for my Hamiltonian, and this n conserved quantity is constructed in a quasi-local. So instead of defining what do I mean by quasi-local explicitly, if you write down these operators in bases of like spins, z spins, they look like the z spin at site I, plus some corrections that these corrections become exponentially small. So this has a little bit of flavor of Anderson localization, but it is much bigger since we are doing something a bit more involved. But so if you are, for example, familiar with Fermi liquid, at low temperature, these tau I are sometimes called the dressed version of this Zi. So the goal is that to show that this perturbative scheme is converging and rigorous if you like to do mathematics, but we are far away to doing that. And these conserved quantities are really conserved quantity of the system. Okay, and your H can be written in terms of this tau I, and which is at the first order diagonal, and the next order are exponentially decreasing as you move forward. That you add more interaction between tau I. So if you take one of these tau I that corresponds to the z component and point I, comparing it to the very far away, the interaction between these two will exponentially decay. And this is a phenomenology that really gives you the absence of thermalization. Okay, okay. So as said, we have a really transition in this model from MBL to ETH, and these kind of transitions are type of transitions that you can see in many systems, like for example in Anderson model in 3D, in some toy models, and this is some sort of a universal structure. When you are in a localized regime, this localized regime shares some feature, namely they have some sort of decay of eigenstates, they have Poissonian level statistics, they have area law entanglements, they prevent you from thermalizing. And in the delocalized phase, you usually have like random matrix statistics, you have quantum diffusion, you have volume law entanglement. So I only say these jargons to say that for people see in very different systems that this transition happened, the localized and delocalized phase can be categorized with a few criteria, that seems to be universal. Okay, so again, come back to this. So those conserved quantities that I constructed for you, people call them local integral of motions. And what is their difference between, so this, okay, if you are familiar with KEM theory, they are similar to the action angle variable in KEM theory. And why there is such a huge fuss about these things? Well, what's the difference between usual integrable system? Because after constructions, because this U is quasi-local, if you add a small perturbation to your Hamiltonian, still you can deform your transformation and again construct some quasi-local thing. So in that sense, these are nice things and they are robust. Okay, so if you want to say that they exist rigorously, it's so there is a work by John Imbrie that it's extremely dense and involved, and it even doesn't prove the thing. It's based on some additional natural assumption, so it's not a real mathematical proof. Okay, and the general idea is some sort of KAM type theory applied to the quantum system. Okay, still, if you ask physicist community people, some people will tell you that this phenomenon doesn't exist and it's all delusion, but most physicists believe that it exists. So now I want to start the model that I'm talking. So you can ask that how robust this MBL phenomena is. So if I have a very long chain that is in an MBL state, I connect it to the bath. And for me, bath is a very toy model of a GOE. So I take a most chaotic system that I have, like 3-4 spins that are as chaotic as you like, namely GOE. I couple it to MBL, and I want to see that is it possible that this bath destroyed this MBL? So this is a rather easy question. So if I diagonalize my MBL in the new bases and do a little bit of computation, I will end up with this toy model. No, yes. So I could have started from this slide really, but I just wanted to give a little bit of motivation. Where does this toy model come from? So if you look at it, so this is a toy model that I have 3 spins. This Hn is IID random variable with 0 mean and some variance sigma. Then so this X0 for me is a toy model for this ergodic thing, ergodic spot. You can make this to be a more involved model, but phenomenology persists even for this very simple model. So at point 0, I have one particular spin, and this spin interacting with all my chain. But as I move forward, the interaction strength decay exponentially. So this is probably the simplest thing that you can find. You have some. So the first time that I saw this model, I said, okay, this is ridiculous. There is nothing in it. You have something that is completely free, and you have an exponentially decaying interaction with one fixed particle. Well, I was completely wrong. There is a localization-delocalization transition in this model, which is extremely surprising. So this Jn is also some random variables, but this alpha is a strength of the decay. So this decay can be strong or weak, and there is huge numerical and, again, theoretical evidence that they say that there is a critical value that if you move from 0 and reach to this theoretical value, this Hamiltonian look like the group of localized Hamiltonians, and if you move from this critical value, which is 1 over square root of 2, you start seeing behavior similar to the delocalized system. So the first time that I saw this is a little bit crazy. No? You have something that is exponentially decaying, so you change a little bit the localization length, and then that one spin can basically thermalize all your chain, which is very interesting phenomenology. But okay, now the thing that we prove is about the localized side. So take this Hamiltonian, okay, and then this is some numerical evidence about this crazy thing that I mentioned. So the first thing is that if you take alpha sufficiently small, this Hn is localized, meaning that there is a quasi-local unitary transform that it's diagonal in this sigma I bases, and this is almost sure with respect to the distribution of Hi. There is a conjecture about the weak form of delocalization when alpha is big, namely that you do not see that it's a strong form of localization, but this is not that important. And the real main theorem is that if you take alpha sufficiently small and look at the point process of the eigenvalue of this matrix, and okay, around some specific energy, which this energy should be positive, but again at the highest entropy state, so infinite temperature, and you rescale it with, so you have a 2 to the power n times 2 to the power n matrix, the differences between eigenvalue is typically 1 over 2 to the power n times this factor which corresponds to the density of state at the highest entropy state. So you rescale with this factor, and this process will converge in a vague topology to a Poisson point process that you can write in the Laplace transform way with a Poisson point process with rate 1. Okay, so this is basically the main theorem. So if you are in a localized site, we can prove that we are localized, and again, a bit more, we can even prove that we have Poisson statistics. And as said, if it's the first time that you see that model, you will say it's rather trivial. So you take something that is free and you add the exponentially decaying thing, and you prove things similar to the free model. But I try to convince you that this is not easy at all, because if you take alpha a little bit bigger, you will see a complete different phenomenology, which is like GOE statistics and so on. Okay, so how much time do I have?
9 minutes to 30. So 4 to 25.
What?
You 4 minutes to 25.
4 minutes, okay. So
5 for question.
Okay. So because I will anticipate very small amount of question, I will try to eat a little bit of.
You can eat your questions.
So okay, I will try to say a little bit about the proof. But if at least up to this moment I convinced you that we have a toy model, that for this toy model we prove localization, and this is not, and Poisson statistics, which something that is rather not, which is hard to prove for quantum many-body systems. But okay, let me just, okay, just a few remarks. So again, I spent half of my talk convincing you this is a relevant model. This model will tell you, at least this analysis a little bit, that this MBL is not stable in higher dimensions. That you just should believe me. So this model, it's not really completely out of blue, can have some similarities with some other random matrix model, like they call it hierarchical models. It's called ultrametric ensemble or Rosenberg-Porter model. But our model is a little bit harder to treat because so the number of so the punchline of the proof or the hardness is that the number of random variable that you have grow logarithmically comparing to the dimension of your matrix. So you have a matrix which is 2 to the power n times 2 to the power n. You have n random variable, and this makes most of the tool that you have in Anderson localization or in other random matrix theory very hard to use, basically. Okay, you can do the things more general. I take one single spin at point 0 and I couple it to my whole chain. Instead of one single spin, you can take a path which is small and then do the same analysis. You can change your interaction with x0, xn. So my interaction was given with x0, xn. You can do the exact same theorem that I change this with other type of interaction, but this interaction should be long range, but exponentially decaying. So did this to set that this is a robust result. Okay, this is the main challenge. So just to say a little bit about the proof. So the proof will go in 3 steps. First, we treat the free model with some moments method that is a little bit similar to the random matrix theory types moments method. Then we construct a coupling between the perturbed model and the free model. And okay, so the free model, at the end of the day, you should say that the number of levels, if you define this random variable to be a number of levels in a correct scaled interval, the moments of this converge to the moment of Poissonian. But for a free model, you have eigenvalues rather explicitly. So the key point is that you should try to prove factorization, namely that the probability of, if you have k of them, it can be factorized. But with an easy exercise, you can see that this factorization is not true specifically. So if you have 2 spins, so if you take your random variables to be normal Gaussian for a moment, and then you compute the covariance between two spin configuration, you will see that the covariance will be something of this sort. And this is not zero, so they are not independent. But we need limiting objects, so for those limits, it's sufficient to show that the covariance divided by n is of order 1. And this will be true for two typical pairs. So if you take a Bernoulli measure of rate 1/2, which gives you your spin configuration, if you take two spin configuration which is typical with respect to this measure, this happened for them. So and the other spin, so then the one that are not typical, it's a bit technical to say that they don't contribute. You need a little bit of like Prescamp-Leib inequality or a bit of combinatorics. Then going from Gaussian to general case, you should only use local central limit theorem estimate in a smart way. And going from two spins to more spins, you should redefine this notion of typicality a little bit smarter. Then from free model to the interactive one, we construct a coupling between this free model and the perturbative one. So this goes scale by scale. So at each scale, first we add a free spin and then we add a perturbation. But the punchline is that the typical gap we hope to be 1/2n, because we have a 2n times 2n random matrix. So we hope that the gap, the typical distance between two eigenvalue is 1/2n, and the interaction is much smaller than that. If this would have been true, then we could have lots of gapped level, and we could have rigorous perturbation theory, and that perturbation theory will give you a good coupling. But this being gapped for all levels, this is not true. So the main technical point of work is really this part, that although this is not true that all your levels are gapped, we can show by some tools that the ratio of the levels that are not gapped, that are not singled out by a distance, this can be shown that to be smaller than any epsilon. So again, you can have epsilon times 2n levels that are not gapped, but you can take epsilon as small as you want. And this, we use some tools from potential theory, namely Cartan lemma, which probably first used by Bourgain in the context of Anderson localization, which is not something typical in that context. Okay, thanks a lot.
Thank you very much for this nice talk. Is there any question?
Yeah, so I didn't, maybe you can say something. So you proved that also there is a supercritical regime.
There is a
supercritical regime, so you proved this.
No, so the things that we prove is only in the localized regime. So,
okay.
so we prove that there exists localization in certain sense when alpha is small, and we prove that there is a Poisson statistics for the levels.
Okay. Is there any other question?